Okay, so last time I think we were talking about obviously thermodynamics. We talked about last time a couple of things. First off, obviously, previous to that, we talked about entropy, which is our delta S. Again, entropy is about that disorder that we have in a system. So, as the disorder increases, so does the entropy value. We talked about three types of entropy values, the delta S of the universe, which is our delta S of our system, our reaction, plus the delta S of the surroundings. We talked about how you could calculate each of those, but basically, our system, our surroundings is basically our products minus our reactants. Again, basically go to a table, look up the values, uh, multiply by the coefficients of the balanced equation, and then I'll get you delta S. Delta S of the surroundings, as we talked about, is related to the delta H of the reaction divided by the temperature. And again, it has a negative sign there. And as we talked about, sort of that opposite relationship in terms of the sign of delta H and sort of the sign of the surroundings delta S. Again, exothermic giving off that energy being negative for delta H. That negative and the other negative there turns our delta S into a positive, which again is what we would predict to happen as the surroundings picks up some more energy, as we talked about last time as well. They're going to create a lot more disorder out there in the surroundings. And vice versa, obviously, if the system is sort of picking up the energy from the surroundings would be more negative in terms of delta S. Again, it is going to be losing that energy and kind of creating a lot more order. And adding both of these together, obviously, if this is greater than zero or positive, then again, that reaction is spontaneous. We then got into Gibbs free energy, which is basically our delta G. And remember, there's a few different equations that we sort of solve for delta G. One delta G, you could really calculate the same way as everything else. Basically, take the products minus the reactants. Again, here, if you're just given an equation and pretty much nothing else, you go to a table, look up your delta G values, and again, adjust with the coefficients and take your products minus your reactants. We also saw one that basically involved a couple of the other sort of thermodynamic properties like delta H minus T delta S. Again, if you have the delta H value or delta S value given to you, you can calculate the delta G value, obviously, sort of directly from those numbers. Or obviously, if you calculated each of those numbers, you could calculate the delta G value from that. Um, the delta G value is basically energy available to do some type of work. So we can use sort of the delta G value. If it is negative, means that the reaction is typically spontaneous, heading towards our product side. If it is a positive value, kind of the opposite there, is non spontaneous, basically heading towards our reactant side. Now, remember, as we sort of talked about, what you want to do is, sort of use the equation, especially with delta G, to basically figure out, what's given to you, I guess is the way to put that. So you kind of want to use whichever sort of information that's given to you to sort of pick the right delta G sort of equation. We also saw that in addition to telling us whether or not this reaction is going to be spontaneous, this equation here, we can also use it in a situation where if the reaction turned out not to be spontaneous at a particular temperature, we could use it to help us understand at what temperature would it turn spontaneous. So we did a calculation like that as well. And that again is basically by saying we need delta G to be negative, so we set delta G equal to zero, and we did some rearranging here and basically solve for temperature, which is the delta H over the delta S. And that allowed us really to sort of calculate the minimum temperature at which the reaction would turn spontaneous. So again, that's sort of another application there that we could use to help us basically determine that. Any questions on that there? Okay. So if I'm not mistaken, I think this is where we left off, I hope. So we're going to talk about Gibbs free energy and phase transition. So we talked a little bit about it the other day as well. So when we talk about phase transitions, we're talking about things going obviously from, say, solid to liquid, liquid to gas, and vice versa. And we talked a little bit about the idea of the energy required to do that, are sort of a reminder, right? So as we go, say, from solid to liquid, or liquid back to solid, that happens right at the normal sort of melting point or freezing point of a substance. And again, there is a certain amount of energy required just to do that transition. And again, that is the delta H of fusion. And again, we're not changing the temperature because it does occur at the same temperature. So the common example, right, is water at 0 degrees Celsius. Again, we get that transition that occurs going in whichever direction you're going, solid to liquid or liquid to solid. But again, we don't change the temperature. And it's really not sort of a jump into the other state to get just a little bit above, for example, 0 degrees Celsius in water, or a little below 0 degrees Celsius in ice. Right at 0 degrees Celsius, where this transition occurs, you basically have both phases in equilibrium with each other, right? So they're in equilibrium at that point. Same thing happening as we do that transition from liquid to gas, right? Or gas back to liquid. That typically happens at the normal boiling point. And that also has a certain amount of energy associated with that transition, which is the delta H of vaporization. And same idea, this occurs at the same temperature and exactly at that temperature. And again, the water, as an example, at 100 degrees Celsius, again, you have both phases basically in equilibrium with each other. And again, not to get a little bit above or below, that you sort of get that transition occurring. So we can use this information and this idea here to basically figure out, you know, what is the entropy change that's occurring during these phase changes. Because this is an equilibrium process, whichever sort of transition you're talking about, our delta G would equal 0. So remember, delta G will equal 0 in an equilibrium type process. That gives us basically this part of the equation still left over, which if we sort of rearrange this and solve for delta S, we kind of subtract it to the other side and then divide by delta S gives us delta H over T in this particular case. Now, we could use this to figure out what is sometimes referred to, for example, as the entropy of vaporization. This is basically the entropy change that's happening as we do that basic sort of transition that's occurring. So if we look at something like water here, again, transitioning from liquid water to gas, basically steam. If we do that little rearrangement there, and we actually put in our numbers that coordinate with that, and just to let you know what these numbers are, delta H here is the delta H of vaporization for water. That was, I think I put up there the other day, roughly 2260 joules per gram, and that's basically kilojoules per mole. This is the normal boiling point, right, for water. Which is 100 degrees Celsius plus a 273, gets you your 373 Kelvin that you see here. So again, we could use this sort of equation here, and we will get this number here that I kind of scribbled on. So let me erase some of that there, of 109 joules per Kelvin in this case. Get rid of some of that so we can actually see the number there. And what that tells us is we do see a increase in the entropy as we're doing this transition, and that's what we would expect to occur, right? As we are going from liquid to gas, we're going from a state of more order to a state of more disorder, which means we would expect a delta S to be a positive number, which is what we do see here. Now, what would happen if we were actually talking about specifically going in sort of the reverse direction, and it was implied that you're doing something like condensation, right? So condensation would imply that you're heading in this direction, going from gas back to liquid if you did something like condensation. You could kind of find the entropy of condensation if you want by basically doing the exact same calculation. But what would be different here is the entropy, I'm sorry, the enthalpy of vaporization, spit that out, would actually be a negative number, right? Because it is releasing energy as we go from gas back to liquid, and our T would still be 373 Kelvin. We would end up with minus 109 joules per Kelvin. And the important part here is the negative part. We would expect, right, the delta S to become more negative as we are going in the opposite direction in the condensation sort of realm, going from more disorder to less disorder or more order, and we would get the negative. So we could do this again to calculate sort of the entropy change that's happening as we do these sort of phase changes. And again, going in the direction like we've sort of talked about previously, from solid to liquid to gas, that's definitely an increase in disorder. And we would expect at those sort of phase changes that the delta S become positive, and vice versa if we're heading in sort of the opposite direction. We would be increasing the order, and we would expect the delta S in those cases and those phase transitions to be negative as we increase the order. Any questions on that there? Now, one note before we sort of leave this slide here, and it's an important one, and it's something that people oftentimes sort of screw up, I guess is the way of putting that. And it has to do with an equation that we saw earlier. So if you remember an equation we saw earlier, which I just wrote on the previous slide, delta S of the surroundings is minus delta H over T. That should not be confused with what we did here, where we rearranged this equation for a phase transition, no negative. Yes, so negative here again with surroundings. If you do the rearranging of this equation, you get no negative here. Yeah. So again, sometimes people either put the negative in both places, no negatives in the place that should be a negative. So again, remember, talking straight, surroundings entropy should have a negative. If you're sort of rearranging the solve for entropy using sort of the delta G equation to figure out something like the phase change, there's no negative. Any questions on that there? Okay. So why don't you give one a go here and see what you come up with. The enthalpy of vaporization mercury is 58.5. Normal boiling point is 630. What is the entropy of vaporization? So take a second and see what you come up with. Okay, so let's take a look here. We're looking for the entropy of vaporization, which is our delta S of vaporization here. We're obviously doing a phase change at the normal, we're given the normal boiling point here of 630 Kelvin. So again, because we are at this phase change and equilibrium, our delta G here will equal 0. That will allow us to rearrange this equation like we did just a second ago and basically solve for our delta S, which again would be of our vaporization in this case. We would put in our, 58.5. I'm going to times it by 1,000 just to convert it to joules, divided by our temperature, which is 630 Kelvin already in Kelvin. Again, this is the enthalpy delta H of vaporization. That's going to get us, we got there 58.5 times 1,000. Again, 58.5 times 1,000 divided by 630, looks like we get something like 92.9 joules, which again would be what we would anticipate it being, as we are really talking about here going from liquid to gas in this case. So we do get this positive delta S value for the entropy increase. If we were talking about going the other way, and they would specify that they were talking about going the other way, they would probably mention something about condensation or something like that. The only real difference again would be the sign here. This would end up being negative, which obviously would turn that guy into a negative, and then obviously at that point, you would have sort of the correct signage, if you will, for our delta S, which would be negative if you're going in the opposite direction, as we would be increasing the order. Any questions on that one there? Also, really important to remember as well that although water is a very common example we use a lot, and we have those sort of numbers in our head like 0 degrees Celsius is the melting or freezing point, and 100 degrees Celsius is the boiling point. If we're not dealing with water like we are not here, we're obviously dealing with mercury, it will have a different boiling point, melting point, and those type of things than water. And obviously here, this value for delta H is specific for mercury and not water. So sometimes, because water is sort of used a lot as an example with heat of fusion, heat of vaporization, kind of boiling points, melting points, and those things. Sometimes people think those are the numbers you should always use. Obviously, those numbers change if you're talking about a different substance. Right? Questions on any of that there? Okay, then let's talk about our good friend equilibrium, because I feel like it's a long time since we talked about K. So let's add to our ever growing list of delta G equations here. And let's add this one, which is the delta G is equal to the delta G naught plus RT natural log of Q. So again, you may be asking, what's the difference between those two sort of delta G's? I think I might have touched upon it the other day, but again, if you kind of look at the little knot there, kind of implies usually sort of standard conditions. And if you remember, we talked about standard conditions the other day. Temperature basically means it's 25 degrees Celsius. Pressure, if you're dealing with any type of pressures, is 1 atmosphere. If you're dealing with concentrations, it's 1 molar in terms of those things. And those are sort of considered kind of table like values, standard condition type values. So this delta G naught here would typically be calculated by going to that table and doing your delta G naught of your products minus your delta G naught of your reactants. So again, looking up the values, doing your products minus your reactants. R here is our gas constant, and it is the one that involves energy. So it's the 8.314 version. T is our temperature, which obviously has to be in Kelvin. And Q is our normal sort of Q, which is the reaction quotient. And remember, that is pretty much calculated the exact same way that we calculate K, which again is our products basically divided by our reactants. Obviously, we take the coefficients into account like we normally do and put them as exponents and things of that nature. So that leaves us really sort of this delta G. And again, one way you could kind of think about it, maybe not 100% correct in all aspects, but one way you could kind of think about it is this is sort of what the delta G would be under sort of non-standard conditions. So there's like something not right in that sense. There's maybe a temperature that's not 25 degrees. Maybe you're doing something where pressures aren't all 1 atmosphere, or maybe you're doing something where basically the molarities are not all sort of 1 molar. So you can basically see the effect on the delta G, by playing with something like concentrations or pressures or temperatures. Perhaps you may have a reaction that started out as being spontaneous and having a negative delta G, but maybe you're able to turn it into a positive delta G, or vice versa. Maybe you have one that started out being non-spontaneous, but by playing something with the pressures, temperatures, concentrations, you may be able to kind of turn that reaction into a spontaneous sort of reaction. So that is one important sort of equation there, which again is our delta G is equal to our delta G naught plus RT natural log of Q. And again, a couple of things that are oftentimes missed on this one is actually the plus here. People always want to subtract on this one for some reason. I think I know why, but people always want to kind of subtract on this one. But again, it is a plus in this case. Now, if we actually get to equilibrium conditions, we do end up with a couple of things that occur to this equation. And at equilibrium, the delta G will equal 0. And at that point, we would no longer be talking about Q, which is the reaction quotient, like are we at equilibrium or not at equilibrium? Obviously, if we are at equilibrium, then that would basically become our equilibrium constant. And rearranging the top equation gives us another delta G equation here, where the delta G naught is equal to minus RT natural log of K. So they're basically built off of each other, these two equations. And again, you could add that to basically the other delta G equations that we had, which was like this way. And basically this guy, right? So as I mentioned before, there's a lot of delta G sort of equations sort of happening along the way here in this chapter. And again, best piece of advice is kind of what I mentioned earlier. You kind of want to pick the one that kind of goes with the information that's in the problem. So what I mean by that is obviously, if it mentions something about equilibrium, something about equilibrium constant, you should go with that one, right? Maybe it gives you some pressures, some concentrations, and things of that nature. You're probably going to go with this one. Maybe you're not given anything other than the overall equation. You're probably going to go look it up in the table. And like we talked about before, you got maybe a delta H or delta S given to you, then you kind of want to go with that one. So that's really the best approach in terms of, sort of figuring out, when should I use what equation or, what should I be using. So that's a good way to just kind of think about it, is basically kind of do it based off of sort of what information is given to you. Questions on that there? All right, I'll skip that, I think. So looking at this equation, we could kind of think about it kind of like the other equation that we looked at with delta G. We could kind of think about, what sort of values would we expect for all these things and how they're sort of interrelated in terms of their values. So if we look at the delta G one in relation to the equilibrium constant, we know a couple of things, which is first off, if our delta G is negative, we would expect the reaction to be spontaneous, which means it is going towards the product side. And if it's going towards the product side, we should have a lot more products perhaps than reactants, which means we would expect the value of K to be kind of large, if you will. Opposite would be true if we had a kind of a delta G that was positive. That would imply that the reaction is non-spontaneous, which means it is probably hanging out towards the reactant side, right? Which means when it's hanging out towards the reactant side, when we do products over reactants to calculate something like K, we would probably expect K to be a small number, right? Or a larger number. So they really do sort of tie together like you would anticipate. Obviously, if delta G equals 0, then, you kind of have a pretty equal miss there happening in terms of the equilibrium constant. It'll be really close to 1 probably in that case. And reactants, our products, are sort of equally favored at that point. So remember, in our normal sort of K situation there, in terms of it being a large or small value, will really correlate really nicely to our delta G in this case. All right, so why don't you take a second here and see what you come up with. Calculate the equilibrium constant for the following reaction, and you have a value there on the bottom that would probably be helpful for you. So take a couple minutes here and see what you come up with. In this problem, if I were to sort of approach it from the start, I obviously see something here that mentions equilibrium constant, and that automatically makes me think I should use, again, our delta G that involves the equilibrium constant, which is this guy. And let's think about sort of the information given to us. We do have obviously 25 degrees Celsius, so we do have a temperature. Remember, R is a constant, which is our 8.314 joules per Kelvin per mole. We obviously are looking for K, which means the one thing that we are sort of missing to sort of allow us to get there is the delta G naught. In this case, we're really not given any other piece of information other than the equation, which means I would go to a table basically first off and look these values up so I could do products minus reactants. So that is again how I will get to our delta G naught. Once I do that, then I pretty much have everything I need to solve for K. So doing that, our delta G naught here again would be our products minus our reactants. Again, going to the table to do that means our delta G naught would be our products, which is 3 times O2's value from the table, not listed on the bottom, but if you remember, delta G values for things in their standard state, like O2, is going to be 0. So it's going to be 3 times 0, minus our 2 times the value for ozone there, which is 163.4 kilojoules. And that will end up getting us 2 times 163.4, a minus 326.8 kilojoules for our delta G value. Any questions on that so far? So we really are looking for K here. So if we do a little rearranging of that equation and solve for the natural log of K first, that would get us that the natural log of K is equal to our delta G naught divided by RT, and we should not forget that there is a negative there as well, right? So we want to make sure we have that. So we also want to make sure, like we talked about a number of times, especially in this chapter, is units. So here I laid up kilojoules, a reminder that R is in joules. So again, you need to do some type of conversion there. Otherwise, you're going to be off. So it's your option, whichever way you want to do that. But again, I'm going to actually convert my delta G into joules, and I'm going to do that by multiplying by 1,000 here. I've also got my negative for my delta G and my negative from down there as well. So we're going to divide that now by 8.314. And our temperature, obviously, we do need to convert that into some Kelvin. So we're going to plus a 273, going to give us a 298 Kelvin. All right, so we got some units there canceling, and basically we will be left with here in terms of a number 326.8 times 1,000 divided by 8.314 and divided by 298, going to get us a 131.9 here is equal to the natural log of K. At this point, we want to get rid of the natural log, so we're going to do a little E action there of both sides. That, remember, when we kind of E this side, just takes care of everything there and makes it K. And if we do that, we do end up with, hit the right button there, that would probably be helpful. We end up with, we'll call it 1.9 times 10 to the 57. That's our equilibrium constant, capital K. Question on any of those steps along the way? Does this sort of make sense? Well, we know a couple of things, right? We see a negative delta G, which would imply probably this reaction is spontaneous. It would also imply that products would be favored. Since products are favored, we would anticipate a larger K value as we do products over reactants. And I would definitely say that qualifies as a large number there for K. Any questions on any of that there on that particular problem? Okay, I'll let you try another one here and see what you come up with. Calculate the delta G naught for the following. The KSP is 1.7 times 10 to the minus 6. Okay, so again here, looking at this, we want to calculate the delta G. We obviously have an equilibrium value given to us. So again, it would make sense to use our equation that really has both of those guys in it, which is the same one from the previous still. In this case, we're actually looking for this guy. And in this one, we have pretty much everybody on this side given to us. So not too bad, just kind of a plug and chug into there, and we will go with our delta G naught is equal to minus our R, 8.314 joules per Kelvin per mole. Our temperature also converted into Kelvin is going to be our 298. Natural log of K, which was given to us, it's a KSP. Does it really matter? It doesn't. Remember that, all Ks are pretty much equilibrium constants. KSP, Ka, Kb, Kw, they're all basically the same thing, products over reactants. So we go 1.7 times 10 to the minus 6. So putting all those numbers in and multiplying, basically 8.314 times our 298 times our natural log of 1.7 to the minus 6. Going to yield us a positive value of 32914 units here would be joules. And in this case, since it's delta G, we could kind of turn it into kilojoules, 329 kilojoules in this case. Any questions on that calc? Actually, 32, I'm sorry. 32, I'll count, right? 32.9, there you go. 32.9 kilojoules in terms of the answer. Any questions on that calculation there? Now we could also, again, kind of, see, does it make sense? So when we look at our delta G value here, we definitely got a positive number, which would imply probably not so much of a spontaneous reaction. Also imply that the reactants are favored here. So since we have more reactants than products in this case, when we do products over reactants, we would expect a small value of K, which obviously our KSP value is a small value of K. So again, all these numbers sort of make sense with each other when you think about, the relationship between, the signs that we see for delta G and sort of the values of K and so forth. Any questions on any of that there? All right, one last example here. Let's see what you do there. So here we're looking for the delta G in this reaction. I sort of given all the information in there, some of those pressures given to you. So take a few minutes and see what you come up with. Here we got some different pieces of information given to us. I see a delta G not given to us. We're looking for a delta G. I got some pressures given to me. So again, that makes me think about the equation that has two delta G's in it. And again, delta G equals delta G naught. Again, it is plus here, RT natural log of Q. In this case, they actually did give us straight out the delta G, which would have been found by going to a table. R is a constant. I see 25 degrees for my temperature. And let's talk about Q. So a reminder that Q is basically done the exact same way as you would calculate K, which means Q in this case would be the concentration of HI squared divided by the concentration of H2 times the concentration of I2. In this particular case, though, we're actually dealing with pressures, which means technically it would be the pressure squared of HI divided by the partial pressure of H2 divided by the partial pressure of I2. So remember, just like in equilibrium, you could use concentrations, you could use pressures. Really what we're looking at here is more of like a KP type situation, but we are calculating Q. So we really do have that information as well. So we pretty much have everything we need. We could just kind of plug straight in if you want. Again, we do have some unit issues between this guy and this guy, kilojoules and obviously joules. So I'm going to once again take the delta G and times it by 1,000 to convert it into joules so that it's all in the same unit. We're going to plus our R. And again, this is the reason I just did that, because this guy is in joules. Our temperature, adding our 273 to it, gets us a 298 Kelvin. The natural log of our Q. So the partial pressure of HI in this case is 0.23, and we want to make sure that we do square it. We're going to then divide it by our H2 concentration, which is 4.26, and our I2, which is 0.024. Any questions on that setup there? All right, so I'm going to kind of clean up maybe the right-hand side here a little bit of the plus sign. So we're going to take 0.23, we're going to square it, going to divide it by 4.26, can also divide it by 0.024. We do a little natural log of that, and we're then going to multiply it by 298 and multiply it by 8.314. It's a lot, but what we end up with, if we kind of clean up to the right of the plus sign, minus 1632.5. Coming to the left, obviously 2.6 times 1,000, going to give us 2,600 equals our delta G. Now finally cleaning it up there, 26 basically minus 1632.5, going to get us 967.5. My units would be joules here since I did some conversion. Do you want to make it into sort of kilojoules like it normally is for delta G? That would be 0.96. I guess we could round it to 8 kilojoules. Any questions on that particular problem there? So what do we see here? We see that under standard conditions, the delta G naught is 2.6, which is positive, which means it's really going to be non-spontaneous and sort of go towards our reactants. And we see by kind of playing with the pressures, we're still in that situation basically, right? We have basically our reactants there as we end up with a positive value. This would also be reflective in probably what we see in terms of the partial pressures. We look at the major pressure there, that is H2, which is over here on the reactant side. And again, that would sort of fit with what we see here of this reaction being non-spontaneous and really sort of hanging out there on the reactant side, which would imply that you'd have probably more H2 guys flying around and contributing more to the pressure. Any questions on that there? Any questions on this chapter? That should wrap this chapter of thermodynamics. Okay. All right, so if there is no questions on this chapter, what we're going to do is roll to the next one. We're going to change gears a little bit, and we're going to talk about electrochemistry. So again, the notes are up there on Canvas if you need it. So here we're going to talk basically about, as it mentions, electrochemistry, which is basically redox reactions. And up front, we're going to sort of go over redox reactions a little bit. We're going to talk about oxidation numbers, again, how to assign those properly. We're also going to talk about balancing redox reactions. Again, in my experience, depending on sort of maybe who you had for first semester, maybe you did a little bit of this, maybe you did a lot of this, depending. So just to make sure, again, everybody's sort of on the same page in terms of redox reactions and stuff like that, we will sort of go into sort of the basics and then get into really what the chapter is about, which is sort of galvanic cells and that type of electrochemistry. So let's start with sort of electrochemistry. These processes are basically what are referred to as oxidation reduction reactions. They are also sometimes referred to as just straight up redox reactions, which pretty much means the same thing. Redox reactions means oxidation and reduction, or reduction oxidation. And let's talk about a little bit about those sort of definitions, and just to make sure everybody's sort of on the same page in terms of that. If we talk about something that is being oxidized or going through oxidation, there's really sort of three definitions. One is we lose electrons. Other ones are you gain oxygen as you go from reactants to products, and you lose H2 or hydrogen as you go from reactants to products. For reduction, is sort of the opposite definitions. For reduction, it is gaining electrons. Also means that you lose oxygen as you go from reactants to products, and you gain hydrogen as you go from reactants to products. Now, for us in sort of general chemistry terms, these are really the definitions that we pretty much go with. If you go off to organic maybe next, you will probably see more of these definitions. They apply very nicely in organic sort of situations, but usually more in sort of inorganic situations like what we deal with in this class. Usually are electrons being transferred and gained, or lost and gained is sort of the one that we look at. Sometimes people remember this by Leo the lion goes grr. Loss of electrons, oxidation; gain of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, and reducing is gaining. You could choose both if you like. Put Leo the lion on the oil rig, he goes grr. You don't have to choose. You can use them both if you like. But that's one way sometimes people remember things. So how do we know if something is sort of being oxidized or reduced? And by the way, we kind of use these transfer of electrons, or these electrons that are being transferred, to basically go out and do some type of work on something, kind of, which we'll talk about, kind of pretty much what like batteries do. They kind of do this redox reaction. They send out electrons through a wire, powers your device, and sort of comes back, obviously, in a sort of loop type situation. So what we typically look at is what is referred to as basically oxidation states or oxidation numbers, which we talked a little bit about, I think, earlier on when we were talking about acid and bases. But we'll talk more about it in just a second. But it's sort of the state in terms of for that element. I don't want to say charge is maybe the wrong word there, but it's sort of the charge that it has in that arrangement. So when we look at something like magnesium plus oxygen makes magnesium oxide here, on the left-hand side, when we have anything that's pretty much by itself, uncombined, it has an oxidation number of 0. Here. When we look at oxygen, which is obviously the way it naturally comes, it really has an oxidation number of 0. When they actually combine, the metal and the non-metal, that is when they actually pick up some charges, and the magnesium has a oxidation state of +2, oxygen has a oxidation state of -2. Now, sometimes people really struggle with, is this thing being sort of oxidized? Is this thing sort of being reduced? So there is sort of a simple way you could kind of determine what is going through oxidation and what is being reduced. And you can just kind of really visually sort of see it by doing just a simple number line, actually, like a number line. On one side of 0 is usually positive numbers, right? On the other side is negative numbers. And let's think about what happens when somebody loses electrons. When somebody loses electrons, they now have more positives than negatives, protons than electrons, which means when they lose electrons, they become more positive. So if you find yourself moving on the number line in terms of oxidation number in the right direction there, going towards the positive side, that means whatever you're looking at is going through oxidation. When somebody gains electrons, they obviously have now gained more negatives than they started with, which means they typically become more negative, which means they would be moving in this direction here, and it would be going through reduction. So that's a very simple way. You could just kind of move across the number line one way or the other, and you could very quickly sort of determine what is being oxidized and what is being reduced. So for example, if we look at if we look at magnesium here, magnesium is starting at 0, ending at +2. So if you just go to number line goes, 0 is here, +2 would be heading in this direction. That tells me that the magnesium here is going through oxidation. And by the way, once you sort of determine that the magnesium is going through oxidation, the oxygen in this case would have to go through reduction. So they always happen together. So if something is being oxidized, there is something that's being reduced. And just to prove it to you, if we look at oxygen, it's starting at 0, ending at -2. So if we go to our number line here, starting at 0, going to -2, which would be in this direction, it is going through reduction, right? It's becoming more negative. So again, this is a very kind of simple approach that you could take to help you identify, what is being oxidized and what is being reduced, just by, again, is it becoming more positive or is it becoming more negative? And that's a visual way you can kind of do that. What does that mean is we can actually split this reaction off into what is referred to as half reactions. And half reactions is a reaction that implies an oxidation reaction and one that implies a reduction reaction. So basically, since we know that the magnesium is going through oxidation, it will be given off electrons. And that would represent our balanced oxidation half reaction. How do I know this is a oxidation half reaction? I know that from oxidation electrons on the product side. So we see electrons there on the product side, and that's an indication that this is a oxidation reaction. It's like the electrons are being given off, they're being lost, so they're like a product, so they're being like sort of released, if you will. On the other hand, we have our balanced oxygen half reaction on the bottom, and that would be our reduction half reaction. And again, we know it's a reduction half reaction because the electrons there are on our reactant side, like they are being gained. So they're being added in, if you will. Why is this a balanced half reaction? First off, they're called half reactions because if you take them and you add both of them together, electrons should always cancel out. So that's an important thing. When you take two half reactions, the number of electrons in each half reaction should be the same number. If they're not the same number, then you do need to make sure you multiply the half reaction by a number to get them to the same actual number. Because the idea here is they should always cancel out, because when you have a redox reaction, you always have an oxidation reaction followed by a reduction reaction that occurs. And what is happening is the electrons are transferring from one place to the next. So there does need to be the equal transfer of electrons, basically from your guy being oxidized to your one being reduced. So when we do that, we are left with really the overall reaction. And again, that's why they're called a half reaction, because when you put them together, you get the overall reaction that will take place. They're also balanced like a normal equation. Each of these guys are balanced just like you would balance a regular equation, which means I have two magnesiums, I have two magnesiums. In addition, they're balanced by charge. Overall charge on the left-hand side is 0. Overall charge on the right-hand side is 2 times +2 is +4. 4 times -1 is -4, for a grand total of 0 on the right-hand side. So whenever we're dealing with sort of redox reactions, half reactions, balanced overall reactions, those are always the two important things to make sure that you actually did balance it correctly. It should be balanced like a normal chemical reaction. You have the same number of elements on both sides. And it should be balanced in terms of charge. You should have the same charge on both sides. And to illustrate that the charge on both sides does not have to be 0 on both sides, it just needs to be the same number. If we look at the oxygen half reaction, overall charge on the left-hand side is -4, coming from the 4 electrons. Overall charge on the right-hand side is 2 times -2 is -4. So again, they don't have to be 0, the overall charge on both sides, but they do need to be the exact same number on both sides. Any questions on that there? Okay, so again, as I said, we could add these back together, and our guy that is losing electrons, again, will be the guy going through oxidation, our guy gaining electrons, the guy going through reduction. Another example here is our calcium oxide formation. And again, a couple of things looking at this guy. If we look at the oxidation state of calcium, again, uncombined here, so actually has no charge. Oxygen in a standard state is 0. When they do come together, the calcium, the oxygen, calcium then I guess with +2, oxygen is -2. So again, if you're not sure, you could look at the little number line and see that calcium is starting at 0, ending at +2. So going through oxidation, calcium. Oxygen, much like the previous one, starting at 0, ending at -2, going through reduction, right? And we have our balanced half reactions. Again, same number of electrons on both sides. We could bring everything down. Everything on the left-hand side stays on the left side of the arrow. Everything on the right-hand side stays on the right-hand side. Electrons cancel, giving us our overall reaction that is happening here in this particular case. Now, when we talk about something being oxidized and something being reduced, it is sometimes confused by people when we start talking about what is known as the reducing agent and the oxidizing agent. So those are two sort of different things in a sense. What is being oxidized is maybe different than what is the reducing agent and oxidizing agent. So let's talk about what those guys are and sort of what that means. When we talk about an oxidizing agent, it is actually the substance that is being reduced. So the oxidizing agent is the guy that's being reduced, while the reducing agent is the substance that is being oxidized. So you may say to yourself, that seems kind of backwards in terms of those names. So let's just talk about two things here. Let's say we had A plus B. And let's say that this guy was going through oxidation. This guy was going through reduction. So what does that mean? Well, it means that A is going to basically give up electrons over to B. When A gives up electrons over to B, that means B can now accept those electrons and get reduced. So what effectively A is doing in this example is causing the reduction of B, hence why it is known as the reducing agent, because it's basically supplying the electrons that's going to allow B to go through reduction. Now, when we talk about B in this case is going to go through reduction, which means obviously it wants to gain electrons. The only way B can gain electrons is to cause A to go through oxidation. And that is why B would be known as the oxidizing agent. So it is basically because that is the effect that they cause in the other substance. So when somebody goes through oxidation, they're pretty much giving away electrons, which means they're causing somebody else to gain electrons and be reduced, and that's why they're known as the reducing agent. While again, as I just mentioned, the guy that's actually picking up those electrons going through reduction, the only place it could get the electrons from is somebody else that has to go through oxidation. So again, the easy way, I guess, to remember it is it's opposite of the name. So if you want to identify the oxidizing agent means what is being reduced. If you want to identify the reducing agent, it is what is being oxidized. And by the way, you find those guys on this side of the arrow. Yes. So this side of the arrow is where you find your reducing agent and your oxidizing agent, not the product side, because that's already done at that point. So we find those guys on this side. So in the previous example, for example, there we looked at our calcium. Our calcium was going through oxidation, which means it's going to be the reducing agent. It's going to cause oxygen to be reduced. While oxygen was being reduced, the only way it could gain those electrons again is to take them from calcium, and it's going to cause calcium to go through oxidation, and the oxygen would be known as the oxidizing agent. Any questions on that there? All right, so if we look at this example here as well, there's a couple of things that we kind of look at. But first off, we could look at two ways to figure out what's being oxidized and what's being reduced. First off, we could do it here because we actually have a tin, and that's a metal. So tin would have, in this case, a +4 charge. Again, oxygen is -2, and there's two of them. That's basically tin 4 oxide. This is tin all by itself, which is 0. And again, if you're not sure, you can look at your number line and go, okay, tin started actually at +4 over here, and he's ending at 0, which means it is going through reduction in this case. So we know that the tin here is actually going through reduction. By default, that means that the carbon should go through oxidation. And what would that mean in terms of our reducing agent and oxidizing agent? That would mean that the tin here, tin 4, is actually our oxidizing agent. The carbon here is actually our reducing agent. Any questions on that? This is also an example. If you didn't do it based off of tin, you could actually do it based off of the idea of gaining oxygen from reactants to product. If we look at the carbon, no oxygens. Carbon on the other side has oxygen. That's a definition of oxidation. Remember that other definition of oxidation: gaining oxygen or losing H2 from reactants to products, are again the one that we typically look at, which is losing electrons. Again, reduction, as we talked about earlier, opposite of that, losing oxygen, gaining hydrogen, and gaining electrons, which is mainly what we look at here. You could even look at the tin in that sense, right? The tin actually started with oxygen, ended with no oxygen. It actually lost oxygen along the way, which again is another definition of reduction. So in this case, you could actually kind of look at both definitions and see what's happening in this particular case. Any questions on that there? Again, probably easier if you have something with sort of a charge or oxidation state that you could look at. It's maybe an easier way to figure out. But again, you could always use the other definitions. And like I said before, we probably don't come across it very much in this class. You do come across sort of the oxygen hydrogen one a lot, like I mentioned before, in organic chemistry. Any questions on that so far? So how do we know these things? Where clearly, as you could be seeing, the oxidation number or the oxidation state is really an important aspect of, what is being oxidized and what is being reduced. So the oxidation number, again, is sometimes referred to as the oxidation state, is basically the charge the atom would have if basically all the electrons were sort of completely transferred. So when we assign oxidation states or oxidation numbers, you should remember that it is not necessarily the charge you typically think of when you do an ionic compound. It could be, but in a lot of cases, and in some cases, it's not necessarily always the same thing as what we think about, when we put together, say, sodium chloride. We think sodium is +1, which it always is, but we think of chloride as -1, for example. As we will see, chloride, for example, can be -1. It could be +3, +5. It could be plus numbers, minus numbers when we talk about oxidation numbers. So sometimes people get fixated on the fact that, hey, I learned nomenclature and they told me, hey, chlorine is always -1 no matter what the situation is. And that is absolutely true in an ionic compound. But if you're dealing with a molecular compound that has chlorine in it, it may not be It may not be the -1 sort of oxidation state. So you got to think about it as sort of the charge it has in its sort of present location and how it's sort of bonded to others is what we think about in terms of oxidation numbers. So there are some rules of assigning oxidation numbers. So first off, as we sort of talked about in a couple of slides ago as well, anything that's in a standard uncombined state, really a free element, has an oxidation number of 0. So if you have a piece of sodium metal, potassium, if you got hydrogen gas, oxygen gas, again, not combined with any other element, how it sort of naturally comes, will always have an oxidation state of 0. So that's why earlier when we did oxygen, obviously I started with 0 for those guys. And like we started with magnesium, that was all by itself was 0 as well. Anything that is a monoatomic ion, the oxidation number will equal the charge. So a lot of things like you normally would think of the charge will be the oxidation state. Things like lithium is +1, sodium is +1. You know, if you had something like iron 3 chloride, which is an ionic compound, we would have our normal sort of charges or oxidation states for these guys. The iron would be +3, the chlorine would be -1 in this case. Oxygen is usually a really great place to start with when you're assigning oxidation numbers and sort of work your way around. So oxygen kind of starting with it is a really good deal. It typically is -2. There is an exception, and that is actually in hydrogen peroxide. And that is because it is the peroxide ion, which is O2 2 minus, is -1. So if you had something like H2O2, which is hydrogen peroxide, in this particular case, oxygen here would be -1, hydrogen would be +1. That gives you +2 and -2. Everything's balanced in this particular case. When we talk about the oxidation number of hydrogen, it is +1, except if it kind of is bonded to a metal in a binary compound, like it comes second. And in that case, it would be kind of like what you learned in nomenclature. We would call this lithium hydride. Here, the lithium would be +1, the hydrogen would be -1 in this case. So, in the rare case where lithium actually comes after a metal, you would have hydrogen being -1 in this case. Otherwise, it should be +1. As I mentioned earlier, group 1 and group 2 are their normal sort of fixed charges, if you will, in oxidation states. So +1 for group 1, +2 for group 2. Fluorine is going to be -1. The other important thing is when we add up all the oxidation numbers for a molecule or ion, it needs to equal the charge. So if the overall charge is 0, when you add up the grand total of everybody's oxidation numbers, you do need to end up at 0. If the overall thing is an ion and it has a charge of, say, -1, when you add up all the oxidation numbers, it does need to equal -1. So let's take a look here at bicarbonate, which is HCO3 minus. So in this situation where you have something like this, where you got kind of 3 elements, first off, the overall charge on this guy is -1, which is what the total of all the oxidation numbers need to equal. So a lot of times when you do this and you got something like this and you definitely have oxygen involved, that is a great place to start. So we will assign oxygen as -2 oxidation state. There are 3 of them, which kind of gives you a -6 that's happening. Now, in a situation of 3, a lot of times it's good to start on the right-hand side, go all the way to the other side, and then finish up with the guy in the middle. So if we go to the other side, we have hydrogen, which is +1, which gives us a +1 charge. And that means that the overall guy needs to equal -1. So we have basically -6 and +1 is -5 in this case. That means to get us a -1 overall charge, the carbon actually has a +4 oxidation state. So +1 and +4 is +5, and +6 is -1 left over. So those would be the oxidation numbers for each of these. And a very important thing is how you write the oxidation numbers. And that is, if you were asked what is the oxidation number for hydrogen, you should write +1. You should include the charge, not just write 1. When you write it for carbon, you would obviously also include the charge, which is +4. When you would write it for oxygen, very much people always screw this up. They want to write, well, the grand total is -6. I want to write -6, and that would be wrong. It would just be -2. Also, again, including the charge. So you always want to include the charges, even if it's positive, on oxidation numbers. And you want to just give it for like one individual sort of element by itself, not like the grand total. So again, oxygen here would be -2, not the grand total of -6. Any questions on that there? All right, so why don't you take a couple minutes here and identify the oxidation numbers for each of these guys and each of these sort of compounds. So we're getting to the end here. Let's take a peek here and see how we're doing. So first off, we got lithium oxide. Nice thing about ionic compounds is, and assigning oxidation numbers is, these guys usually will end up just like our normal sort of process here of charges. Oxygen would be -2 in this case, and lithium, which is group 1, would be +1. And again, +1 and 2 of them is +2, and -2 equals 0. So lithium here +1, oxygen would be -2, like you might expect. Here we're looking at PF3. This again is not an ionic compound, but this is actually, right, some bonding happening here, some covalent bonding. Fluorine is always going to be -1. That means there's a grand total of -3, which means the phosphorus here is actually going to be +3. So the phosphorus here would be +3 in terms of its oxidation number. Fluorine would be -1. Again, here we normally think about, when we think about ionic compounds, phosphorus being a -3 charge. But in this arrangement here, by sharing electrons with the fluorine, it's actually picking up more of a +3 arrangement. Also remember that when we think about -3 for phosphorus, that's when it is attached to a metal. Looking here at HNO3, again, starting with our oxygen, which is a good place, that's -2. That gives us a -6. Hydrogen being +1. In this case, the overall charge is 0, which means the nitrogen does need to be +5 in this case, which means oxidation number of hydrogen +1, nitrogen +5, oxygen, again, not the grand total, but just -2. Same idea with nitrogen. We sometimes think of it as -3 when it's hooked up with a metal. In this case, not hooked up with a metal. In this covalent bonding, takes on sort of a characteristic +5 sort of charge. Any question on that there? Looking at the last one, which is dichromate at polyatomic ion. We're looking at oxygen, which is -2. There's actually 7 of them, gives us a -14. In this case, it does need to equal -2 overall. Here we're looking for what the chromium is, and there's actually 2 of them, which means if you want to just do a math problem, that type of deal. But basically, each of the chromiums does need to be +6. +6 times 2 is +12, -14 is -2 left over. So chromium here +6, and the oxygen -2. Any questions on how to assign those oxidation states or numbers? Any questions on anything we talked about today? Okay.